So orbital motion continued. The last thing I said was the Earth, and you have satellites put into orbit of different kinds. Some satellites are very close to the surface of the Earth, just barely 300 miles from the Earth's surface. So those are meant for weather, spying, all the other research purposes. Okay, so mostly they're all research purposes that they kind of scan. How long does it take approximately to go around once?
24 hours.
How many?
Like 90 minutes.
Around 90 minutes, which is around 1.5 hours. Roughly. Depends on the height. Like I think for the height of around 300 miles, we got it as close to 90 minutes, right? So most of the satellites which are actually spinning around, getting information, they're all going around in sort of 90 minutes. Once in 90 minutes. And that is basically your time period. Time period, capital T. That's 90 minutes. Of course, time period should be in seconds. When you're going to put things down, you cannot keep years or hours or stuff. You have to put everything back to. So all right. So we discussed those satellites which are actually moving around so close to the Earth's surface, which are meant for those purposes. And then the geosynchronous satellites are the satellites which are actually moving around. In fact, they are all more on the equatorial path. So that is why if you're in the northern hemisphere, as we are, most of our dish antenna will be more facing towards the south, southeast, southwest, that sort of. We won't be facing to the north. So that's the Earth, that's the equator, and that's where they are mostly spinning. And if you are on the equator, you look straight up. But not necessarily straight up, because it may not be parked right there, it can be parked there. So then like that. So it basically has to go that way. Whereas if you are in the northern hemisphere, then you're facing more towards the south, east, or west, that sort of. If you're in the southern hemisphere, then you're facing to the north or northeast, that sort of. Okay, get it? So the dish antenna that you're supposed to be facing is... So still I'm drawing it this way, but understand it is supposed to be the equatorial thing. So it should be definitely put into an orbit at a certain height. That's your height. And that's your radius. And what's so special about this particular position that the satellite is put in? The importance of that position is that it goes with the Earth. In other words, can I say the speed of this has to be the speed of this one? Speed? Anything on the Earth, like we are moving at a speed, and this one should be moving at the same speed. Is that right? Or what is wrong there? What can be right? How can you put it in such a way that it is right?
It takes the same amount of time to go around, but it's not the same speed because it's further out. So then
that is true. Definitely, it is not the same speed. It's faster because it's further out. That's correct. So, but if I want to say something in terms of speed, what can I say? These two have the same what speed? Angular speed, angular velocity, or angular speed, omega. So this has the same omega as this. They both are spinning together. That means how long it takes for the Earth to go around once is the same time that one should take to go around once. So they both have the same omega. Speeds are of course different. Now what are the forces that are going to come in here? One is the gravitational force, Fg. And what are the forces?
FC? Well, FG is FC.
Fg is Fc. Fc is not a new force. Again, understand that centripetal force is not a new force. So this is the only force that is acting on an orbiting satellite. And this provides the necessary centripetal force. Yeah. This provides the necessary centripetal force. So the centripetal force is for it to go around and round is Fg. Now centripetal force I'm going to write in terms of mr omega squared. Now R is this. The capital R is the actual radius of the turn taken. You get it? It's not R, small r is not h. The radius of the turn taken is r plus h. So I'm putting it as capital R. Is equal to G m over r squared. Now, what is the small m representing here? Mass of the satellite. And the mass of the satellite goes off there. That means no matter how much mass the satellite has, it doesn't matter as long as the most important thing is the height. Now, you can leave all this as it is and work it out, or you can even replace capital G and capital M with small g and small r squared. You can do that. Okay. So if I want to replace it that way, then r omega square is equal to g r squared over r squared. And what is omega? Omega is 2 pi over capital T. Turn back a couple of pages, you'll see that equation. Omega is theta over T, and theta is 2 pi for one full turn, and T is the time period for one full turn. Yes?
Did you cancel out an R on the left and you just make it R on the bottom?
I can't cancel that.
Oh, never mind. Sorry.
One is on the top and one is at the bottom.
Sorry.
Two, okay, so they won't cancel.
What did you say the capital R stood for?
Capital R is the actual radius of the turn taken by the satellite. The radius, this circle's radius, this one. So when you're actually using, when you're trying to find out what is FG, the G mm over D squared, the D is supposed to be the entire radius of the turn. So how far is the satellite from the Earth's center? That's what it is. So that's why you put R here. And when you're using centripetal force, m r omega square, what R are we talking about? The radius of the orbit, which is also R. Get it? So this R over here is the distance between the satellite and the Earth's center, which is R. And this one is the radius of the orbit of the circular path, which is also R. Now, when you put omega 2 pi over T into this, what do you get? R 4 pi square over T square, is that okay? R 4 pi square over T square. I'm substituting omega here. Is equal to G R square over R square. Cross multiply that equation, you get T square times T square times GR square is equal to 4 pi square R cubed. From there. T is the time period of the orbiting satellite, which is same as the time period of the Earth, which is
24 hours.
24 hours. So we know T. And we know G on the surface of the Earth, 9.81. This one?
That's right.
This is 4,000 miles converted, 6.4 times 10 power 6, but squaring it. And 4 pi square is a constant. So all these are known to us. So can you figure out exactly where it is supposed to be?
I just got a question.
Yeah.
So GM is equal to GR, right?
GM is GR squared.
Oh, GR squared. Okay.
Remember that equation. That's a very, GM is GR squared. You don't have to use this, but I just used it here. But you can leave it as GM itself. So if you use G and M, this whole thing is going to be G and M. G is a constant which you already know, and mass of the Earth is a constant. Yeah.
Lowercase g, is that always going to be?
That is going to be only on the surface.
fall on the surface then? So
The lowercase, this equation that you're writing here, what is capital G? It is 6.67 10 power minus 11. This one is the mass of the planet that you're talking about. This is the acceleration due to gravity on the surface of that planet. Make sense? And this is the radius of that planet. Doesn't have to be only for the Earth. Universal. If you say, all right, I want to find what is the acceleration due to gravity on the surface of the Sun, then capital G is fixed, 6.67 10 power minus 11, mass of the Sun, or radius of the Sun, and G will be the acceleration due to gravity on the surface of the Sun. Makes sense? So you can use this equation for any planet, any asteroid, anything. What acceleration due to gravity does it have on the surface? This will tell you. That's why that's an important equation. And now I just use that equation here because we can just replace this with that if you want. Because sometimes they won't tell you what is the mass of the planet. Instead, they tell you the acceleration due to gravity on the surface of the planet and the radius. So then just get rid of these two with that. Make sense? So it depends on what is given to you. So all right, so we have this here. And you know that all these are constants. This is a constant, and this is a constant. So you end up with this equation. No, you end up with this proportionality. The time square is proportional to r cubed. The time square is proportional to the cube of the orbital radius. And this was actually stated by Kepler. Kepler said this. Now Kepler is another physicist who actually kind of investigated how much time this star takes and this moon takes and stuff like that. So he was basically looking at the sky and doing all his timing and stuff like that. And then he ended up coming with some interesting conclusions. And his conclusions were, although he did conclusions, it was more like Kepler's. Yeah, we can call it Kepler's laws, because he came up with that, but how true it is going to be, is it exactly this way? He did multiple examples of different other things, going around. See, they didn't have anything to do after 6 p.m. Unlike you all. You're all so busy with the phones, with the internet, because you have light, and you go to bed around 12, 12:30, 1 o'clock. There is no control at all. But those days, people, they go to bed, 6 o'clock. Sunset, there's nothing else to do. Why do you want to burn the oil and, waste resources? So they'll just put off the lights. They normally have a bed outside, nice weather, good outside. So they put the beds outside, lie down. What they're seeing is just stars. So they see the patterns of this star and that, all the constellations they come up with. Now there's no time for us to look upwards at all. It's always downward. You're always looking downward. There's no chance that you're looking upward anytime. But even if you attempt to look now, you don't see anything because of the pollutions and stuff like that. The sky is not clear. You hardly see stars. Why? Because it's polluted and a lot of dust. So, basically the sky has changed into a foggy thing. So if you want to really see the stars, you have to go to a place where it's absolutely clear, like a mountain top. You go on top of mountain and look up, you'll see all the stars. And you can see this constellation and that constellation and all those things that people have said earlier. You'll see all the stars. But now from here, less likely, unless everything's clear. Even then, you're only seeing some of the brightest ones. You don't see the dimmer ones. And if you're going to go to a satellite like that and look up, definitely you'll see very clear stuff. There's nothing to stop you. So once you cross the 300 miles atmosphere, then it's all very, very clear. That's why any telescope that is mounted here on Earth's surface has limitations. And that's why they have the Hubble telescope, which is actually a telescope on a satellite. So once you go out of the Earth's atmosphere, then Hubble's telescope is able to see everything crystal clear. And so any conclusions that you can make. But anyway, So Kepler and Newton, all these people didn't have any other resources. They were not even having electricity. So therefore, they will be looking at all these things and coming up to conclusions. So Kepler actually came to this conclusion by what? So Kepler's laws are these. He said every planet goes in elliptical orbits. That's his first conclusion. Every planet goes approximately in elliptical orbits. The second conclusion he came up with is so elliptical orbits is like that. So he says, what Kepler said is the area that is swept by the radius, the area swept by the radius is the same wherever it is. So if it is moving here, it will sweep that much area. In other words, here it's going slower, and here it's going fast. All right? So in other words, over here it has more angular speed, and here it is less angular speed. So it covers a smaller angle here and larger angle here in such a way that the area of this is the same as. So the line joining the planet and line joining a satellite and a planet, those, or line joining a planet and the sun, those lines. So this line sweeps out equal areas wherever. Because the closer it is, the faster it is. It has to be faster because of a certain conservation. We'll see that conservation later. Conservation. And you can see that the closer something is, the faster it goes. Right? So if I do this, now watch. The closer it gets, can you see that it's going faster when it comes closer? That's pretty much it. When it is further away, it is slow. But when it gets closer, it speeds up. That's exactly what's happening there. All right, so that is Kepler's law. All right, Kepler came up with the second one that way. And then he investigated further the time periods and all those things and approximate distances. They could only do some approximations on distances. And then he found out that there is a kind of proportionality, and the proportionality is t squared is proportional to r cubed. That was Kepler's law, 3 laws. Now, when Newton actually mentioned his law, when Newton came up with this universal law of gravitation saying the force of attraction is proportional to the product of the masses and inversely proportional to the square of the distance, when he said that, he was not really sure. He just guessed that distance square concept. He guessed that distance square part of it. And also he guessed that the whole thing is circular, which is not true also. So if you try to dig deep into it, Newton's law is not the real thing. More realistic thing is the Kepler's. So anyway, Newton just assumed it is going to be some square, because in magnetism and electrostatics and everywhere you'll see the inverse square relationship. So he thought, okay, for gravitation also that inverse square relationship should be true. And so he came up with that. And then he tested it out for the moon, because for the moon he knew that it is coming every 27.3 days, So he applied to the moon those equations, and then he ended up getting this. Like this, exactly what you're doing right now. He ended up with this equation, and he said, isn't that what Kepler said? Yes. So which means I'm right. And Kepler is also right. You know what I'm saying? So that's exactly his conclusion. So he assumed an inverse square law, and then he started working with that inverse square law. He just went on, and he bumped into this equation. As soon as he came to this equation, he just said, isn't that what Kepler said? That means I should be right and Kepler should be right also. Never thought about both are wrong. So he proved that Kepler must be right, and he self-confirmed that d square inverse square proportionality that he took for granted is also correct. It's interesting how these people actually worked with certain things and made some laws and postulates, and we are following that now. But now we have more practical evidence of the fact that they are correct. Because when you apply that to different satellites, different planets, they work out right. Anyways, I'm just mentioning about the Kepler's law there, but our focus is not on this. Our focus is to find that. So what is r cubed? It's t squared g r squared over 4 pi squared. And therefore, you can take the cube root of r, so it's t squared g r squared over 4 pi squared to the power of 1/3. I'll give you some time. Go ahead and plug all these things in and get the answer, or try to get the answer. Yeah.
Should TV and hours.
42.
Yeah.
Should be 6 minutes.
So you should be getting an answer. So that's what you should be doing. R cubed is equal to 86,400 squared times 9.81 times 6.4 times 10 to the power of 6. If you use, instead of times 10 to the power of 4, use the E function, E operation, like this, E6 squared. You don't even have to put brackets if you do that. If you're going to do this, then bracket is not needed. We can just 6.4 E6 squared. That will work. Divided by bracket 4 pi squared. And that will get you the r cubed. And once you get the answer, then take the cube root of r cubed, whatever answer you get. And the answer should be 4.2, any more other decimals?
2, 3, 4.
I got 2, 3, 4.
4.234?
3, 5.
3, 5, 4.
Okay, 4.235 times 10 to the power of 7 meters, which is basically 42,042.35 times 10 to the power of 6 meters, which is 42,350 kilometers. So you see it's 42,350 kilometers. The distance from here to here is 6,400 kilometers. And they are expecting the distance from here to here as 42,350 kilometers. So what is the height?
3.5 times 10.
Subtract 6,400 from there. No, subtract 6,400 from here. And that will be the answer, which is 36,000,
35,000.
35,000.
950. 950.
All orbiting satellites must be put there. No other place. So all the geosynchronous satellites that you are focusing your dish to, they're all at the same height, but at different spots. There are thousands and thousands of satellites doing the job. Each country has its own, basically. Not one, but many. So there are multiple satellites. Now, what are those satellites used for? What are those satellites used for? The geosynchronous satellite. TV, communication. It's the communication satellite, basically. So if you're calling your friend sitting in this room, guess how the signal is going to go? You're taking your phone and calling somebody. When you call somebody from here, that signal is going to your provider's tower. It goes to your provider's tower. And once it goes to your provider's tower, then it shoots it up to here. Because you don't know where you are. Your friend could be on this side of the earth. You understand what I'm saying? Your friend could be on this side of the earth. So if you're here and your friend is here, signal is not going to go straight from here. Signal goes to your tower, and your tower shoots it all the way there. Now, there is hardly any loss when it goes from here to here. There will be some loss only by the atmosphere. But after that, look at this distance. This distance is a lot. So all this is absolutely no loss. It just goes without any loss. The signal goes. So the signal goes all the way here, gets into the satellite. The satellite receives that signal amplifies it using solar power, amplifies it, makes it stronger, and sprays it down again. And now when it sprays down, it goes everywhere. It is showering it from above. So if your friend is here, your friend's tower will pick it up and then send it to you. So it's not straight away.
What if they're on the other side of the world?
Yeah. What if your friend is here? What's this? Can you tell me now?
On another satellite.
Yes, exactly. What is that?
On another satellite.
Would another satellite pick it up?
Yes.
Transfer it?
In fact, there are lots of satellites. Lots of satellites. So that's why, for example, your internet provider is not depending only on one satellite. They kind of pay some money to the other satellites and get one channel from there. So basically, all the providers, they will seek more coverage, and for more coverage, you need more. You need to pay. You can't just use one satellite. So you have satellites everywhere. So, for example, I'm watching cricket from here. How on earth Australia, India playing right now? So there's a cricket game going on. The signal is actually sent to this satellite and it is being showered here. But how am I watching it from this side? It's because this signal goes here. This one shoots it here. So it picks up signals and then it goes down. So signals are kind of spread all over the place. Yeah.
So, like in some like natural disaster or something, when you're trying to get like call someone that doesn't go through, is that because like the signals are overwhelmed, or like what's like what?
One channel, if it is not working, that's enough.
Okay.
If it's a long distance call. But generally, they automatically switch to a channel which is free and open and stuff like that. There's a lot more than what we think. Plenty more. So this entire telecommunication is greatly helped because of these satellites. Without them, there's no chance of corresponding to the others. Now, previously, they used to have cables running under in the ocean. They used to have cables running inside. From one country to the other country and all that, they have cables. And then now that's all gone. Yeah,
How many satellites are currently in orbit?
I don't know. There are millions maybe. Because think of this. US has its own bunch of satellites, but even you can put one in there. There are some people who actually will, you can actually take a satellite. I mean, you can actually it won't cost you much, I think, but they'll make sure that it is put into orbit. And then you can be in correspondence with that. Okay? There are some. I don't know exactly. You can look it up and see. I mean, it will cost you, say, $1,000 or whatever. Maybe a satellite as small as this. So, and then once you prepare it, you pay a certain fee to the people who are allowed, putting it in orbits, and they just kind of place them, and then they are coming back. So those satellites will keep going. And what this can do for you is that you can correspond with it, and you can get some signals from it and stuff like that. You can use it for. I think most of those things, the smaller ones, are more close-up things that you can actually study the Earth's surface better and so on. Not for telecommunication. I don't think it's for telecommunication. It's for these. Now, if they lose their track and start coming down, crashing into the Earth, absolutely nothing wrong. They just burn out before. So all those shooting stars you see, they're not satellites, but they could be one of them. They're not satellites, but they could be one of them. Who knows? Because these satellites are actually basically our sky is polluted with a lot of these satellites. Polluted. Plenty are there. Now, all of them are not expected to go in the same orbit all the time. There could be multiple reasons why they can get deflected. But if a meteor comes and hits it, then it's off track. Once it's off track, it starts coiling into the Earth, and you don't know where it's going to land. You have no control on that. It just keeps coiling in and it passes into the atmosphere somewhere. And when it passes into the atmosphere, just a streak of light, and that's all. Over. So those will burn out ultimately. It won't come down. The smaller ones definitely are not going to reach here. So they just coil inwards, gain speed, and then because of the extreme high speed, as they enter the atmosphere, they just burn off. Okay. All right. So friction actually can do a lot of damage like that. Any questions on this? Just be careful with. I'll give you a question here. Okay, what is the acceleration due to gravity on a planet? Write down this question. Write down the question. What is the acceleration due to gravity on the surface of a planet? What is the acceleration due to gravity on the surface of a planet? Whose mass is twice the mass of the Earth? Whose mass is twice the mass of the Earth? And has 3 times the diameter of the Earth. And has 3 times the diameter of the Earth. That's it. That is the question. What is the acceleration due to gravity on the surface of a planet whose mass is twice that of the Earth and whose diameter is 3 times that of the Earth? So, now this question is a comparing type of question, right? You can see that. We are comparing Earth with
Mysterious planet we have.
some planet. So what you do first is to kind of draw it. Never try flipping pages and looking for an equation. That is not the first approach. The first approach is draw. Okay, here is the Earth. That's the Earth. On the surface, the acceleration due to gravity is g, which you already know. The radius of this one is r. Now this is the other planet, which has got a mass of,
2 times the mass of the Earth.
let me call it MP. Let me call this ME. Just to differentiate. Let me call this RE. And what would be this one? RP. What's the connection between G, RE, and ME? What's the connection? Do you know any equation that connects these three? I boxed that equation and said it's a very, very, very important equation. What is that? Gm is equal to gr squared. I'm going to use that equation. I'm using that equation. So what is the G on Earth from this equation? It is capital G mass of Earth over R of Earth squared. Is that right? I'm just using this equation. The G on the Earth's surface is this. Correct? What is the G on the planet? Similar equation. Capital G MP over RP squared. So I just wrote down the equation. Now what we're going to do is we're going to substitute for MP and RP. We're going to substitute. Or do one thing. Divide this equation with this equation. Just divide it. What do you have? GE over GP is equal to. If I divide this with this, what do you end up getting? G's will cancel out, right? Okay, I'm showing the whole division. This divided by this is equal to GME over RE squared divided by that, which is times RP squared over GMP. Is there anyone who's not clear with that step? I'm dividing GE with GP. So I'm dividing this expression with that expression. So I'm dividing this expression with that expression. I change the multiplication sign here. Now capital G is gone. Now next step, GE over GP. Now I'm going to replace, because I told you that that I gave you the conditions, that MP is twice ME. Did I say that? Yes, Will?
Yes.
And what did I say about RP?
3 times.
The diameter is 3 times. So what will be the radius then? 3 times RE. Diameter changes the same way as the radius changes. So the radius of the planet is 3 times RE. Is that clear? Now I'm just going to substitute. I'm going to leave ME as it is, and I'm going to leave RE square as it is, times RP. What will I put for RP? 3RE squared. So what do you get? 9RE squared. And what do you put for MP? 2ME. Is that clear? I'm just getting rid of RP and I put 3RE and then square it, so it'll become 9RE squared. I'm getting rid of MP because I know it's 2 times mass of Earth. Now see what's happening. ME, ME. RE squared, RE squares. So now your equation is pretty simple. GE over GP is equal to, you're just having numbers here, 9 over. So if you cross multiply this, you get 9 times GP is equal to 2 times GE. So what is GP on the planet? 2 times GE over 9. And now you can put the number. And you know GE is 9.81. So if you put 9.81 there, so you get the answer, 2 point something. So what's the acceleration to gravity on that planet? 2.18 meters per second squared. Just watch how the problem is done. Planning, drawing, those are important. Then you can compare. So these are questions where you can compare and then get your results. Because you're comparing the planet with the Earth. So automatically these equations become very vital. They are important, yeah.
Where'd you get the 9 again? The
Because this RP is 3RE squared. So what is RP squared? It is 9. It is 3RE the whole square, which is 9RE squared. Okay. So instead of RP squared, I'm putting 9RE squared and get rid of all the mass of the Earth and all those things, and then you have a simple ratio. And then you can compare the acceleration to gravity on those planets. Get it? Any other questions? So if you want to find the mass of the acceleration to gravity on the moon, all you have to get is how many times the Earth's mass is the moon, how many times the radius, and then you can actually figure that out. And sometimes the question, can be further twisted. Imagine the same question. If a person can jump, this is not to scale, all right? If a person can jump vertically up, how much can he jump vertically up? Vertically up. 3 feet? Can you show me 3 feet jump?
Yeah,
I can't.
78 feet.
We're talking about a guy. Yes.
Can you jump 3 feet?
I can't.
78
You can?
I cannot.
Who is able to jump 2 feet?
Give me a trampoline.
I'm just gonna. Well, in this universe, you also say you can throw a marker into a movement, so I thought we were.
Universe. Are you saying you can't throw a marker into a orbit? Can you throw a marker into a orbit?
Well, if I had enough strength and all the machinery, and I can do it.
Yeah, so
You don't have to use your muscles all the time. You can
If,
always.
if we're using machinery, I can jump 3 feet with a trampoline.
All right. Now, use your own muscles. Can you jump 2 feet high?
Some people can do that. Not good.
Ooh.
Yeah.
You jump off a ledge.
Yeah, like if I bring my knees up, I might.
Now, don't get confused with this jumping concept. What about high jump? How are people doing this high jump?
Because they've trained. Like, they're all-
Are they jumping all this height? Not really. They're not doing that properly. The thing is, when I say jump, your center of gravity must go up by a certain amount. Now, I can jump from this height. I mean, can I, if I put a bar over here, can I just cross that bar? Obviously. All I have to do is just fall over to the other side. Because my center of gravity is already here. My center of gravity is already here. So all I have to do is just kind of lean and just flip off. And then you're on the other side. And if you have a good landing pad over there, what's worrying you? Absolutely fine. So jumping this height is not at all a problem. So we are so that is the reason why people who do high jump, they don't do high jump like that. They don't do a high jump by standing straight like this, run straight there, and they don't do that. Why? Because if they do that, they are raising their center of gravity far more than what is necessary. So high jump normally they go like this and flip over. So they are horizontal on the bar. Very good. You've seen it. So when the bar is like that, they just come straight like this and then they tilt over and they barely cross over that way. Because center of gravity, you don't have to take it that high. So if you're coming vertically and then jump like that to make your legs cross that bar, your center of gravity should be way up. All right, so when I say jump, and again, when you jump, when you fold your legs, it looks like you're going further up, but no. Look at the center of gravity. So think of one spot on your body, like here, my belly button, and then when you jump, like how much does it go? That much. All right, if you really try, maybe that much. I mean, it's not going to really go too far. So I'm not going to be. I'm talking about a normal person. So therefore, this one, let's say, is 20 centimeters. All right. He's jumping 20 centimeters. When I say 20 centimeters, he's able to raise his center of gravity 20 centimeters higher. Okay? So that is 20 centimeters jump. Question is, if he can jump 20 centimeters on the Earth's surface, how high can he jump on this planet? You get it? If he can jump 20 centimeters on this planet here on Earth, how high can he jump on this one? So what do you have to do here? What do you need to know? How can you find out how high you can go? What's needed? Acceleration due to gravity, which you already have now. Over here it is 9.81, and there it is 2.18.
So would you
And
divide?
now the effort that you're putting with your muscles, the takeoff speed, depends on you. So if it is the same you sitting on that one, then the takeoff that you're going to get out of flexing your muscles is going to be one value, right? So that means you're going to jump upward with a steady velocity. You're going to jump with a steady velocity. So initial velocity is something, and what's the final velocity? 0. And what's the acceleration? So can you connect the displacement, velocities, and all those things together? Go ahead. What equation connects these things? What's the equation that connects displacement, acceleration, initial velocity, final velocity? Yes. Vf square is equal to Vi square plus 2Ax. And this is 0 equals to V square, that whatever effort that you're able to put in, minus 2 times G on Earth times X, which is 0.2. So what you see from here is V square is equal to 2 times GE times 0.2. Is that clear? And on this planet, you're doing the same thing. Your V square is exactly the same. So it'll be 2 times GP times X. So equate the two. because the v squared on this and v squared on this is the same because you are the person jumping. And how high it takes you can be seen from here. So if you equate this with this, we have 2GE times 0.2 is equal to 2GP times x. 2 cancels off, and you know 9.81 is over here times 0.2, and you know this one is 2.18. Or you can even replace that with 2GE over 9. You can do that. This is GE, and that is 2 over 9 GE and x. Because we have 2 over 9 GE as the GP. So GE cancels. You have just a bunch of numbers to tackle. So it's 9 times 0.2 divided by 2. And the answer is 0.9 meters, 90 centimeters, which is that much on the planet. Yeah.
I did this another way. So can't you just do the acceleration like 9.81 divided by 2.18? That gets you 4.5. You multiply that by 20.
Yeah, you can do, but how do you get that proportion? You can't do something without a reason. So going by a kind of proportion sometimes works. Sometimes. It's dangerous to go that way. Going by proportions, dangerous. Because sometimes you'll miss a certain thing like this. You're squaring this, and so 9 comes up there in the equation. So you will be thinking, oh, it's 3 times. But no, it's just 9 times bigger in terms of square. Right? So, yes, logically, if you want to solve a problem, I'm not discouraging you from using a proportion method. Yes, it's okay, but it's not too safe. The best way to do it is like using equations and get a concrete answer and then go from there. And so since we already got this relationship, I'm using that right there. And we end up getting the right answers. Now, since we got this number, that's why you're able to do it. But if the question was worded like this, the planet has a mass twice of the planet has a diameter which is 3 times that of the Earth. If a man can jump 20 centimeters on the Earth, how high can he jump over there? So what you have to first do is get this. And then go for this. Right? You have to do 2 things. Well, I'm not saying all these are there for the test, but just you should be able to stretch to any level. Once you know gravitation, you can just go ahead and not only use gravitation, but extend it to equations of motion when needed. So you cannot limit to only gmm over d square as gravity. No, there's plenty more. Okay. Let's do some other questions. A coin is placed 11 centimeters from the axis of a rotating turntable. You know what is turntable? Okay, you place a coin there. It's placed 11 centimeters from the axis of a rotating turntable. So as soon as you read that, you can actually start drawing the picture for that particular thing. So turntable, and that's the axis. And the coin is sitting somewhere. And how far? 11 centimeters. The coin is sitting 11 centimeters away. Rotating turntable of variable speeds. That means you can increase the speed and keep going faster and faster and faster. When the speed of the turntable is slowly increased, the coin remains fixed on the turntable until a rate of 36 RPM. You can imagine this? Any physics problem you should be able to imagine straight away. So when you say turntable, yeah, you can now see a turntable right in front of you, the coin sitting right there, and then it's starting to spin, and the coin is still staying in one place, and you make it faster and faster and faster. It is supposed to come off sometime. Now think of you, take a quarter, put it on top of one of the fan blades. One of the fan blades, you keep it somewhere. and you turn the fan on, initially you will see the coin is still moving with the fan. And you increase the speed of the fan. As the fan becomes faster and faster, it will finally come off. Why is it coming off?
Because the static friction is being overcome by the acceleration.
That is also correct. Yeah, that's correct. So in other words, the coin is coming off because of the lack of the required centripetal force. And the centripetal force was provided by friction, but you cross that limit. Once you cross the limit, it slides off. And that's exactly like this. So when you're trying to spin this faster and faster and faster, at one speed, it comes off. So they said 36 RPM. 36 RPM. Is that omega? Revolutions per minute. You have to change it now to? So what is omega? Get omega from there. So 36 revolutions per 60 seconds. And that means 36 times 2 pi over 60 radians per second. So you get omega from there. 36 RPM, 36 revolutions per 60 seconds, 36 times 2 pi, for every revolution is 2 pi radians divided by 60. And so you have, whatever is the answer here. What is it? Yes.
1.2.
1.2.
Yeah.
3 point? Radians per second. So when the omega becomes that, it comes off. So now let's look at the forces acting on it. Force acting on it is friction. And that provides a centripetal force. So friction should be equal to centripetal force. And what's the formula for friction? Mu times the normal reaction, which is mg. If it's a horizontal thing, the normal reaction is the mg because the weight is downward and the normal reaction is same. You get it? So the weight and the normal reaction are same, so that's why I'm putting it as mu times mg is equal to Fc is a centripetal force. I'm going to use omega now instead of speed. So mr omega squared. M cancels off, which means it doesn't matter if it's a quarter or a dime. Doesn't matter. Mass gone. So whatever you place on top, doesn't matter. So what is mu s? Is equal to r omega square over g. Now you can plug things down. R is 0.11. Omega square is 3.77 square over 9.81. And that will give you 0.16. The coefficient of static friction between that coin and the turntable is 0.16. And the moment it slips, the coefficient reduces further than that, therefore there's no chance of it settling down again. Once it slips, it's gone. All right. Questions on this? So you can see over here, we're just using centripetal force provided by friction concept. But then we are bringing the omega into it because they gave you 36 RPM, so we are trying to get omega from there and use this equation rather than mv square over r, because this is not v. But you can get v from there also, you know that, right? V equal to r omega, we can actually get v from the omega and use mv square over r. But you can continue this. Any questions on this? Yeah. Tarzan plans to cross the gorge by swinging in an arc from a hanging vine. If his arms are capable of exerting a force of 1,400 newtons on the vine, what is the maximum speed he can tolerate at the lowest point of the swing? And his mass is 80 kilograms, and the vine is 5.5 meters long. So he's crossing over 2 points, and the vine is hanging like that. So what is that? 5.5 meters long. That's a vine, and he's 80 kilograms, and he's swinging like that. Okay, yeah.
Could you repeat some of the last part of the question?
If his arms are capable of exerting a force of 1,400 newtons on the vine, in other words, the tension, what is the maximum speed he can tolerate at the lowest point of his swing? Why they're saying the lowest point of the swing? Because that's the place is fastest. That's the place that's going to be fastest, because as it comes from here, acceleration due to gravity is pulling him faster and faster. At this point, he's fastest, and then it slows down. So if he can tolerate that, everything's okay. So now the vine, we are going to consider that point. And the question is asking for speed. What is the maximum speed here that he can tolerate? So at this point, what are the forces acting? mg. What else? Tension in his arms. Which is bigger? Tension is bigger because circular motion. So tension is greater than mg. So T minus mg is equal to mv square over r. And they told you T is 1,400. He cannot tolerate more than that. And his weight is 80 times 9.8. Is equal to because we are assuming that Tarzan is on Earth. Then 80 times speed squared over what's the radius of the turn? Solve this equation for velocity, that's it. Okay. 6.5 meters per second. That's the fastest he can tolerate there.